Good morning. I welcome you all back again for our vehicle dynamics class lectures of this winter semester. See that in the last class we essentially looked at vehicle handling, particularly the stability analysis of our LTI system. So the vehicle model, bicycle model, what we were considering is linear time invariant system is what is very important. So for such system, you see that raw stability criterion is that AC criterion. Just looking at the characteristic equation of your system, you would be able to talk on the absolute stability of the system. In case it is not very important of absolute stability, you can have correction in your control system of your vehicle model, looking at what is its relative stability factor, or it's called the steady state error in the system. So if we are able to get such an information, then your dynamic behavior of your system can be very well predicted, and that would help you to talk on stability of your system. So the advantage of raw stability criteria that we have seen, sometimes though all the coefficients of your characteristic equation polynomial are positive, but you need to investigate using raw stability criterion array. So how do you fill the elements of raw this array, and then using that, how do you talk about the stability of the system is what we have essentially seen. Since our bicycle model for handling study is of 2-degree freedom system model, second order ordinary differential equation, so your input essentially is steering input. So you would be able to solve such a second order system stability analysis straight away. That is where when we apply raw stability criterion, we were able to look at stability factor, and the stability factor is negative, suppose with the vehicle parameter values, then that vehicle tendency is in handling is what is called an oversteer tendency. And that oversteer tendency would be pronounced in the vehicle when the initial condition of your vehicle or there is a sudden disturbance that is coming on your vehicle happens. So what do you mean by initial condition or sudden disturbance? If your vehicle is being ridden on a straight line motion, and suddenly you have a disturbance coming from wind gust in the side lateral direction, then the vehicle would behave how? Is the vehicle is going to be stable or unstable? That is what you have to say. So if the vehicle is stable, what do you mean by that? Even though the wind gust is acting on your vehicle, your vehicle remains in its equilibrium state of straight line motion, then you say that it is stable equilibrium as ensured of your vehicle. In case if your vehicle is critically stable, means what? Your vehicle will have some oscillation. That oscillation of your vehicle would be what in bicycle model is yaw frequency oscillation. So in the top, if you look at, the vehicle would oscillate like that, but meanwhile it will come back to its straight line motion. Then it is what is called stable system. But if this oscillation is continuous forever, then it is called critically stable system. Continuous forever means sudden wind gust is coming, as long as that disturbance is there, you see that or after the disturbance, your straight motion, you have this oscillation, then you are going, then it is critically stable system. What is an unstable system? In case of this wind gust is acting and your vehicle response is going unbounded and it doesn't come back to its equilibrium of straight line motion, and that is what is called an unstable state. So that would easily pronounced in oversteer tendency vehicle. So if your characteristic equation, the stability factor value is negative, such vehicle will definitely undergo this unstable state when the speed of the vehicle is critical. So that is what we were looking at. That is how you should interpret the stability of your vehicle. If the same vehicle is of understeer tendency vehicle, what would happen? The oscillation would be there due to the disturbance, but that oscillation will continue forever, means it can go to a critically stable system, or the oscillation dies out because of the damping property of vehicle quickly, then you can call that as a stable system. So this is how you should be able to say. in case we have a lot of assumption in your bicycle model, that is tire cornering stiffness are constant value. So you consider tire as a linear model. You not consider suspension effect. So when you do not have such a realistic thing, what would happen sometime when your system is unstable means the response of your system would go, so that the linear system, linear time invariant system would become non-linear system. At that point of time, this bicycle model or these equation, whatever that we have in our hand, is of no use. It cannot predict the actual dynamic behavior of your system, and the model of the system become non-linear. So these are all something that you should understand. What do you mean by dynamic response of the system? Looking at the dynamic response of the system, you should be able to talk on the vehicle stability, whether it is of absolute stable system or it is of relative stable system, or is there any steady state error that are present in your system. So that's what you have to see. Okay, so this is on one hand. If you look at in practice, the vehicle will not, vehicle is designed for how, based on a control system. A modern vehicle is having control system design incorporated. ABS is incorporated with the control system design, right? So if you are looking at a control system model of your physical vehicle system, so the input signal that is given to the vehicle, whatever that input that comes onto your vehicle, or for example onto the control system, is not known ahead of time, right? That is what does that happen when you drive your vehicle. You are not knowing there will be a sudden disturbance that are going to be there. There can be a big pothole, or there can be sudden wind blow from the lateral direction. So this is all unexpected. So when something which are unexpected input that comes onto your vehicle, you would not be able to predict it dynamic response analytically. Why? Because that is that unexpected disturbance that comes onto your vehicle as an input is what is and random in nature. In such scenarios, you would not have an analytical approach of the system. But however, these systems can be tested with the known testing signal functions like step input function, or ramp function, or an impulse excitation function, that is what is called direct delta function. So these are the functions which are called aperiodic signal functions. So if we have these aperiodic signal functions are given to your model system, and there is a good correlation of your output for this given input, then you would talk on that vehicle or any physical system that it has got good correlation and the dynamic response is in concurrent with the input, so that system would go quickly to the input that you are giving in. So like that you can predict. That is why you see most of the systems are tested with this standard test signals, and then if they are good at these systems, then they would also have a good dynamic response for any unexpected random input. So that is how the researchers or the designers of your vehicle for this control system are working on. So this all kept in your mind. In today's class, we are essentially going to look at such an input, which are called a direct delta function, or a step input function, or ramp function. So what are these functions, input functions? And if you give such an input function to a physical system, how the responses are going to be there is all what in short today's class that we are going to learn. And we have this period, and again at 11 o'clock we have another period. Hopefully I will try to complete this part of that in these two periods, so that we will have one lecture left for completing your lateral dynamics, and that I will do after CAT 2, and then we will get into next module. Right? Okay. So let me share my ActInspire board. I hope you are able to see this board. Right? So in the last class, essentially, we looked at this Rao stability criterion. And here, if you look at this closed loop transfer function, is what is simplified block reduction diagram. So you should understand that it is not open loop transfer function. Sometimes no students do have such doubt. So this is your closed loop transfer function or output input relation, which is a simplified version of your closed loop design system. So what was that we have seen? So we have R of S, and there is a summing point plus minus, and then you had your feed forward transfer function, and that has given you an output C of S, and you take from here and out, and then you had one function called H of S, which is feedback transfer function, feedback transfer function, and from there you take a signal here, that is your what was that, E of S or B of S signal, feedback for signal, and you had here an actuating signal E of S. So this is what is your simple closed loop control system model. So this simple model can be expressed through a simplified block diagram, where I have my closed loop transfer function and an output. So input and output relationship is represented with a simplified closed loop transfer function. How do I get my closed loop transfer function here? If I know this feed forward transfer function and this, so that's essentially going to be G of S is going to be 1 by 1 plus. So we refer this as G of S in closed loop system. Then this is your so this is your output input relationship. That means C of S by R of S. So that would be 1 by 1 plus G into H. So G of S into H of S. So this is what is this transfer function, and that transfer function is what is given by this for a generic case. So keep that in mind. You should not get confused with that. So this happens to be feed forward transfer function will be called an open loop transfer function when this is one that we have seen. That is simply that the output is not going to be dictated by an input. So you give, there is no relationship from there. So you give an input and get an output. That is what is going to give you an open loop behavior. But this open loop transfer function can be corrected to have your output should have a good correlation to your input. Then that would have a feedback signal, and that comes, and that is where we define this output by input relation through this. And if you look at this, you should not mistakenly understood as an open loop system. So this is simplified block diagram of this closed loop system. Simplified block diagram. I think this is what on first day when I was teaching you this thing, Vineet Krishna was trying to tell, sir, this transfer function is in open closed loop system. So to have a clarity, I had a thought why he was to ask like that. Then I wanted to tell this at this point of time. So please have an idea of open loop system design is separate and closed loop system is separate. So open loop system output is not going to be get corrected. It would just give whatever is the nature of your system. For any input, there is an output. There is no need of having a good correlation between an output and input in open loop design of your system. Whereas closed loop system, I want a good correlation of my output to the input. So I would take the feedback and I will go and do correction, and then I would improvise my transfer nature of my system so that I would have a good correlation of output to input. So this is what we are going to look at today's class, right? So we were just looking at this characteristic polynomial equating to zeros, what is called a characteristic equation. If we have characteristic equation, you would be able to talk on this stability, absolute stability, by preparing such an array. And we have looked at, of course, the different case example problems of fourth order system and third order system. Third order system with, if we have zero element in the column, what to do. And you have a fifth order system example where you have one row in your array comes zero, then you need to take an auxiliary characteristic polynomial that would be just above whatever is there to this S3 row, these elements should form a coefficient for your auxiliary polynomial. Then differentiate that polynomial, take that as an next that as a replacement for S3 row, and then you continue this process, and then you talk on your stability to find out are there any roots of this characteristic equation lie on the right half plane. If that happens, then the system is unstable, that you can conclude. And in such cases, here you are playing with your numbers fixed, but you can have these numbers of coefficients in physical system are going to have some parameters influence. If you play around with varying those parameters, you can make this system to be stable. So you would be able to have a conditional requirement or the parameter limitations and so on. So that is what is a classical example in our bicycle model we have seen. A bicycle model of oversteer tendency can be stable system when I have my critical velocity is not reached, right? Till then, I would have my system in the stable state, right? So that is what we have understood. From stability point of view, how do you look at yaw plane model, our bicycle model, using Rao's stability criterion? Right. So today's class, let us go ahead with the understanding transient and steady state analysis of the system. Right. So this is lecture number 33, and today's date is 17/04/2021, and we are going to have today's class transient and steady state response analysis. So if you look at our simplified block diagram of our closed loop system that just now I have explained you, this is my input and this is my output. This is closed loop transfer function. When I write, you should say that it's a closed loop system. There is feedback from output all there, and it is a simplified representation of my closed loop control system design. If this control system design output response is C of S, the input response is R of S, or R of S. So my C of S in time domain. So here it is your response in Laplace thing. So it's a polynomial, this is a polynomial. Whereas in time domain, if you look at my output C of t would have two parts of my output. So what is it? So how do I get C of t if I have C of S? Laplace inverse transform of this is what is C of t, right? So or you can have a convolution integral and then you would be able to have it. This. So it is simple. Output as function of time would have two components, C transient of t as function of t plus C steady state function. So two solutions that you get. So any response output would have two output solutions. One is called a transient response, END, transient response. Another one is called a steady state response. Steady state response. So what do you mean by transient response? So transient response means the system goes from the initial state to its final state. So what do you mean by transient response? The system response or system goes from its initial state to its final state is what is called a transient response. What is steady state response? So steady state response means the manner in which the system output behaves as t approaches infinity. So the system behavior as t as the time t approaches infinity. So that is what is called a steady state response. So that's what is that we were able to tell in our Laplace transform, that as t tends to 0, that means s tends to infinity, and s tends to 0, that means t tends to infinity. So initial and final value theorems are used. So we will see that in a while. So before that, I would like to give you set of formulas which were required for your study, right? So though we were remembering, let us list down those formulas that would be useful. What are those? Is I have some standard functions and the corresponding Laplace transform of those functions. So let me write down, put those table. So I have my standard function, say f of t, and its corresponding Laplace transform of f of t. What is that it's going to be? So I have a function called Dirac delta function. So what is that? Is called Dirac delta function. So how do you define this Dirac delta function? It can be defined as like this. If this is t, I would have my function which is at t is equal to 0 only. So this is my Dirac delta function. So here, if I have my integration minus infinity to infinity, Dirac delta function delta dt, that's going to be 1. That is how it is defined. So this is Dirac delta function. At t is equal to 0, I give an pulse, and that is the integration from minus infinity to infinity of my time. So minus infinity to infinity. If I integrate, whatever that is there is 1. So it is called a unit impulse function. So if that is my function, its Laplace transform is going to be 1. And we have another function called step function, unit step function. So this function value is say 1, f of t is 1. Then how do you represent that? Here is like this. So I have my function t, and I have from here say 1 unit step function. So when this unit step function can be good input for the signal, if you have sudden changes in your system from an existing state, then this unit step function is going to be more realistic function. If you have your physical system is subjected to some shocks suddenly, then this Dirac delta function as an input, you give and examine its output is an appropriate input function. So if you have sometime your response is gradually varying, then something a function called ramp function is a good function. So these are some standard aperiodic signal input functions that are generally considered in any transient and steady state response analysis of your physical systems. So this is what is called a step function. So at t is equal to 0, I have my f of t is 1. Right? T is not equal to 0, it's t greater than 0. At t greater than 0, is this greater than or equal to 0, it is 1. Our f of t is 0 when t is less than 0. So this is 0 point. So this is how I define my unit step function. So what is the unit step function for your passenger car? So when you drive your straight motion in the skid pad, a very large flat surface of test track, so you go with your vehicle straight and then you give your sudden steering and then you hold it. So that is what is step steer input. At t is equal to 0, you just initially you just give the steering input and then hold it, and that is going to be constant throughout the time. So before you give that input t less than 0, it's 0. So that is an input what is called step function. That means what? I should give delta f some radians, 0.1 radians. When t is greater than or equal to 0, and delta is 0 when t is less than 0, is what is the step input function in a real time scenario. So what is this direct delta function in case of our vehicle? I just give straight motion, I just give pulse and then take back. So at t is equal to 0, that one fraction of second, I just give steering, then I immediately I'll get back my steering to the old position. And that is what is direct delta function. So next function is what is called ramp function. Ramp function, what is that is, when I straight drive, I just gradually increase my variation of my steering. So that means that function would be varying it like this. So this is what is f of t, that's equal to t. So if this is time and this is 0, at t is equal to 0, function is 0. As t progresses, this is gradually increasing. So this is what is a ramp function. And this is my f of t. Right? So this function is what is that is, when you drive your vehicle, you are gradually increasing your steering like that, keep on, and as you are increasing your steering, you are going to take a measurement, and then you get your output response. And these three standard input responses that if you have in your hand, then you would be able to talk on transient and steady state responses. Right? So for this, if these are the three functions that I consider here, and their corresponding Laplace transform, let us look at. So here, it's, if function is 1, then it is going to be 1 by s. Here, if function is t, then I would have here 1 by s square. Something happens to this pen. Right? So I can also have like that, instead of t, I can have t power n. So if I have t power n is my function, I would have here n factorial. Laplace transform of that function will be n factorial by s. Here t is s squared, so it is n plus 1. N plus 1. Right? So I can also have a function. What is an exponential function? E raised to at. So if this is the function, its Laplace transform is 1 by s minus a. So some time back, yeah, s minus a. And then I can also have a function which is exponentially decaying function. So then I would have my Laplace transform is s plus a. Right? And then I can also have a function, a product of time into e raised to at. So if I have this function, I would have correspondingly my Laplace transform is 1 by s minus a square. Minus a square. I can also have a trigonometric functions. That means harmonic functions. So if I have that here, my function, so harmonic functions are the periodic functions, right? So I can have sine at, then what is my Laplace transform is a by s squared plus a squared. I can have cos at, then it is s by s squared. Instead of a for sine, here s cos s for in numerator, and then s square plus a square. And if the function is like that, I can have hyperbolic function. So instead of sine at, it's sine h of at, which is hyperbolic function. Then it is instead of this plus in denominator, it will be minus s squared minus a square. So cos h at, then it is s by s squared minus a square. Right? And then that also let me put what are these two important theorem called initial value theorem and final value theorem. Right? So what is the initial value theorem statement? If time t, limit t tends to 0, f of t, here, then on this side is limit s tends to infinity, s phi of s. That is initial value theorem. And then limit t tends to infinity. So t tends to 0 is what is time from initial time to its final time. Then initial value theorem is used for transient response study. So final value theorem is used for your steady state response requirement. So if this is the function here, then your final value theorem correspondingly is limit s tends to, this is not delta, this is s, right? S tends to 0, s phi of s. So that's going to be final value theorem. So please understand this all. There are some important properties called the resolvent matrix and so on that we will see later again while solving the problem. So now these are the three standard input today's class that we are going to look at for an important system called the first order system, right? For the first order system. So let us now look at, see, we were doing an nth order system for stability analysis, but steady state and this transient response study, I just begin this with looking at first order system, then we'll get into second order system. So what is our bicycle model? Is what is our second order system model, right? So let us just look at, because 2-degree freedom model, our spring mass vibratory system is what is second order system. Right, so we will see that response later after this class, but now we will see first order system dynamic behavior. Right, so what are an example of first order system? So in electrical circuit, RC circuits, if you look at, that is first order system. If you look at thermal system, heat transfer problem, those can be modeled as first order system. So like that, you have physical system which can be modeled as first order system. So first order system would have your transfer function in denominator polynomial. You would have linear function. That is it. How also you can say what is first order system. So let us now look at our first order system transfer function. So that is simplified form of my closed loop transfer function. If I take, so this is my R of s, C of s, this is my R of s, then my C of s by R of s is what is this transfer function here, closed loop transfer function, and that would be 1 by Ts plus 1. What is here T? S is Laplace variable, so order 1, so it is linear polynomial, and this T is what is called the time constant of first order system. So the time constant is very important. The smaller the time constant, the quicker the steady state response. So that's what we will understand now at the end of this. And when you give this input here of some standard input, so my RFS is going to be first my step input, then ramp input, then impulse input I'll give, and then I'll get what is my corresponding output of the system. So in that process, you will see that how are you going to get applying this Laplace inverse Laplace transform to get our responses and so on, right? So what is an important assumption in first order system is initial conditions are assumed to be 0. The inputs are, right? So initial conditions are 0, and input functions are, like we said, unit step input and unit ramp input and unit impulse input. inputs. So these are the inputs that we are going to look at and give to the system and see corresponding output and how they are correlated. Is the response output is going to reach the similar response as that of an input, then the system is stable system. Instead of reaching, if the system is oscillating continuously, then it is critically stable system. Instead, it is not reaching, it is going away unboundedly with a more and more response, then it is called an unstable system. So such an unstable system in physical systems can be prevented by having some mechanical stops, right? Though you have that, with that continuous unstable unbounded response will take a linear system to a non-linear system. That's what at the beginning also I was iterating you, right? So keeping that again in mind, let's continue. Now, what is this first order system? So this is simplified block reduction diagram. So if you have to get that as a model, then it would be like this. So that is also simple. So R of S, and you have this plus minus, and you'll have here feed forward transfer function. So the feed forward transfer function is 1 by Ts. It's not writing. So something happening with this stylus. Yeah, Ts. And this is my output of C of S. And let me take here, and this is going to be a unit step function. Not unit step function, unit means feedback transfer function is of unity function, one function. So here I would have my closed loop transfer function as 1 by 1 plus 1 by Ts into 1. So if I have this, I would be able to have LCM. So it's going to be 1 by Ts plus 1 by Ts. Just a minute. Just a minute. By Ts. Yeah, that's correct. So here it is 1 by 1 plus G of S, that is this into H of S, that's 1. So it is 1 by this, so it is T of S. Sorry, it is not 1 by, it is G of S by, right? So what is my closed loop function is G of S, that is 1 by Ts. As by this, so here 1 by Ts is there, and I also have in denominator, I take this LCM, this is Ts, so this is going to be 1 by Ts plus 1. So this is my transfer function, closed loop transfer function, and this is my simplified block representation of my transfer function. So if I have this is my transfer function, how do I get my response is what we are going to see now, right? So look at now, what is my output? So output is C of S, and that's going to be 1 by Ts plus 1 into R of S. So what is my R of S? I would first take a unit step function. So advantage of representing in Laplace domain or through the transfer function is that the simple product of your functions are sufficient. So if I take my unit step function, I know Laplace transform of this function is going to be 1 by S. So I have to just put this here. So 1 by Ts plus 1 into 1 by S. So this is what is my output response in Laplace domain, or it is my output response in Laplace domain. So now how do I get my C of t is taking inverse Laplace transform. To take inverse Laplace transform, see, this has to be factorized partially. So I will do that partial fraction of this function, and then that would be easier. So I have here 1 by ts plus 1 into 1 by s. So how do I partially factorize that is like this. So I would have this 1 by s into ts plus 1 can be written as a by s plus b by ts plus 1, right? So if I do now cross multiplication, so this is 1. So here it is a into ts plus 1 plus b into s. So now in this I can do, see this I am doing it factorizing it, so that I need to find what are these values of a and b, so that I can write these products of this term into summation terms. So now if s is 0, what is my function? If s is 0, 1 equals a into 0 plus 1 plus 0. So a value is 1. If s is, I have to make, now see, I put s is equal to 0 so that b will not come in my equation. I would get what is a. Now a should not come in equation. So what does my s should be? So if s equals minus 1 by t, minus 1 by t. If I substitute here, it's minus 1, so this term is 0. So then 1 equals, this equation will become a into, right, a into 0, correct, minus b by t. So that says what is my b? b is minus t. So b is minus t. So now put this b equal minus t and a equal 1 in this function. So I have my transfer function now. So or my response, now my response. So you can also represent this as c of s or y of s, any way that you like. So let us take a c of s only. So c of s, that's equal to 1 by s into s plus ts plus 1, ts plus 1. That is now going to be a is 1, so 1 by s minus b is t minus t by ts plus 1. So now I can rewrite this as 1 by s minus this is 1 by s plus 1 by t, and this is my c of s. So if I have my output as function of Laplace variable, I can get the output as a time function by simply taking inverse Laplace transform. Taking inverse Laplace transform, so inverse Laplace of c of s, which is going to be c of t, that's going to be here. So inverse Laplace transform of 1 by s is what is equal to 1. So that's what we were writing down this formula list. See here, if I take Laplace transform of this function, I get this. If I take inverse Laplace transform, 1 by s means I'll get 1. If I have here 1 by s squared means it is t. Like that you would be able to get. So now here since it is 1 by s, this is going to be 1 minus, and Laplace inverse transform of 1 by s plus a. So then it is going to be e raised to minus at. So it is going to be e raised to minus at. So minus a here is what is 1 by t. So t by t, e raised to t by t. So this is what is my output response. So c of t equals 1 minus e raised to t by t is what is my output response for all values of t greater than or equal to 0. Right? So when t value is 0, it is 1. C of t. When t value, correct? If t value is 0, e raised to 0, it's not 1. E raised to 0 is 1. 1 minus 1 is 0. So C of 0 is what is 1 minus e raised to 0. That's 1 minus 1 is equal to 0. So if if t equals time constant t, then it is 1 minus e raised to t by t 1 minus 1. So 1 minus e raised to minus 1 is what is going to be e raised to minus 1 value, you know, that is 0.368, and if I substitute that, it is going to be 0.632. So if I have, instead of t, if I put 2t, this value would be increasing. So now this is what you observe, what are the response value, right? Whereas I know my input is step input. My input is step input. So what is my input? My input was step input. As a function of time, if I put unit step input, so this is 1. So this is my input. This is 0. But my output now is not reaching at immediately this. So it takes some time. So you see here how that is changing. So I have at t is equal to 0, my output response is 0. At t equals to t, I have my output response is 0.6. So I should have ideally the same 1 value if this is well correlated immediately. But it's not so. I get first at t is equal to t value. I get this. So I get this value means somewhere here. It's slightly more than half. So here, when t is 2t, so if I substitute here 2t, then it is going to be e raised to minus 2. So e raised to minus 2 is going to be 1 minus e raised to minus 2 is going to be 0.865. So 0.865 somewhere here. Then if it is of 3t, e raised to minus 3, it's 0.95. So it is reaching this value. So if it is a 4t, then it is 0.982. So it's reaching somewhere here. So this is my expected output, but this is here when it is reached, this corresponding value is 0.982. So it is just 2% less than what is that my input response. So that to reach, it takes 4 times the time step. So how quickly this reaches here is what is going to say my steady state. So what is my transient response from the initial to the final time? So the final time is when it is reaching to its steady state. So if my t value is smaller, this would happen so quickly. So that is what would be this. So this is my response, and that response is going to go reach this 1 asymptotically as this t value increases. So here is what I have my slope. If I draw this, that's going to be this. So if I draw this, that's going to be here. So this is the slope. Just a minute. Let me take black color. If I draw this slope here, so this is 1 by t. 1 by t. Right? So if I draw slope here, that's going to be the slope is gradually changing, and when the slope is 0, then it is going a steady state. So this is how the response comes. So the output would reach its final value when at t equals t, if it is maintain its initial speed of response. That means the slope should not change. This is my slope, and if it maintains in the system at t is equal to t itself, it will reach this point. But what is happening? This slope is not fixed, it is changing. So that's what is called the speed. The dynamic response speed is not 1 by t. Instead, it is increases. It is decreases. Since it is decreases, it takes some time, and then it reaches its steady state. So how quickly it is reaching depends upon the value of t. The smaller this value of t, the quicker the response reaches its final state. So the slope of the response curve decreases monotonically. See, the slope is decreases monotonically from 1 by t to 0 at t tends to infinity, right? So the slope which is 1 by t monotonically decreases and reaches slope 0 at t tends to infinity, right? So if t is greater than, or equal to 4t, you see that it has reached the final value of your step input within 2% error, within 2% of its final value, right? So that is what would be taken. So there is small error or it takes more time. So you would see that it reached that final state when it is going to be 98% and above the response. So this is what does that you understand from first order system, its response for unit step function, right? So it's very interesting that we will look at the responses now for other two. So see, if we have a class, we can proceed anyhow. Let me finish this first order system for two response another 5 minutes. Then you can listen back, right? So if I have my unit ramp system, so case 2, input is unit ramp function, then y of s or r of s, right? Output, right? C of s is going to be what is that? Is transfer function 1 by ts plus 1 into since it is a unit step function, that is t f of t is equal to 1 when t is greater than or equal to 0. Its Laplace transform is 1 by s square. So the similar way, if I apply partial fraction, and then I can represent this as a summation of these factors like this 1 by s square. Leave it to you to work out t by s plus t squared by ts plus 1. So how do you get this factorization? For that, what you have to do is like this. So given transfer function, I just give how do you do, and then you work out ts plus 1 into 1 by s square should be, since there is a order 2 term here, s square term, you should have your functions like this: a by s square, ts plus 1, ts plus 1, right? Ts plus 1 plus bs plus c by s square. So if I have like this, and then if I take this as LCM, I would have my functions like this. So it is going to be 1 equals a s square plus bs plus c into ts plus 1. So in this I can put now s value is 0, so that I would have what is my s value as 0. If I put, I will have c value as 1. C value as 1, right? If s value is 0, c value is 1. If s value is minus 1 by t, I put minus 1 by t, so that this is going to be 0, this entire thing. So I will get a value as t square, right? A value as t square. And then I can get what is my b value by substituting these values. So I'll get b value if I have my a and c substituted here. I would have my b value, or you can put s is equal to 1, and the b value and this if you c and a value if you put, so s is equal to 1 and you have c value and a value, so you would get what is b value. That b value is minus t. So that is how you get your fractions right here like this. So if I substitute that in this, I can get my transfer function is partially factorized in this way. So it's t squared plus ts plus 1 here. and then I can apply Laplace inverse transform. So C of t will be Laplace inverse of C of s, and on this, so I would get my responses for that as this. So t first, because 1 by s squared, so that's going to be inverse Laplace transform is t minus t plus t into e raised to minus t by t. So these are my responses, my output responses, function of time. So then again, it is very interesting here if we are going to analyze your output. So this is what for t value is greater than or equal to 0. So I would get my error signal. What is my error signal? What is the difference between output and input? So output is C of t and input is input minus output in this case, error signal, because input is what is the expected output for the standard input function. So if that takes some time to get because of transient effect, right? So this error signal would be this. So what is my input is R of t minus C of t. So R of t is what? R of t is what is 1. R of t is so second is ramp function here. R of t is t, right? Yeah, t, and this is t plus t minus t e raised to minus t by t. So this goes off. So I'll have t taken out, 1 minus e raised to minus t by t. So this is my error, and this error is what is called the steady state error. Steady state error. So this can be simply understood by looking at this relationship. So let us put that input output in the graph. So let me take time on horizontal axis, and here I'm going to take my input function R of t as well as my output function C of t. So what is my R of t? It's equal to t itself. So as t0 is 0, so it is linear variation, so 45-degree line. So this is my input R of t, that's equal to t function, right? Unit time function, unit time ramp function, unit ramp function. So if this is that, then my output happens to go like this. Output happens to go like this. So this is what is called the steady state error. So it doesn't reach here, it is parallel here. So this is what is steady state error. Steady state error. And if I just extend this down here, I have this is going to be t, right? So at t it reaches. So you can have this function can increase to 2t, 3t, 4t, and so on like this. So here you see this difference R of t minus C of t. So this is your C of t. So if you plot this, t minus t plus t e raised to t by t, it would go in this fashion, right? So when this error is going to be, see this error t here, so this difference is what is going to be t. If this error E of t is going to be t if t tends to infinity. That is why if I extend this line, this is coming to t. The error function is t. So this value is simply t. When it is at t tends to infinity, that is why 6t and so on. So 6t is almost reaching to infinite time. So time step is t. If this is smaller, then the quicker I would go to my steady state error, which is constant, and that would be t when t tends to infinity. So that you can see here. So in this function, if I substitute, it is 1 minus e raised to minus infinity. So e raised to minus infinity is 0. So it is simply t. So my steady state error would be this time constant itself as t tends to infinity. At t tends to 0, what would happen? What is my error? 0. At t tends to 0, what is my error? It is t into 1 minus e raised to 0. So it is 0. So error is 0 at t is equal to 0. But error is reaching to some steady value at t tends to infinity. That is why it is starting from here. So here the value of input and then output is same. Right? So error is 0 at the beginning, but it is at t tends to infinity. Your steady state response, at that steady state response is not exactly matching with this. It is having a difference of t, the time step value. So this is how you are going to look at your response for this. So the third response in place of input, if I put the direct delta function, what is that I'm going to get? So case 3.
Excuse me, sir.
Yeah.
Sir, we have another class now.
Yeah, I just have announced no 10 minutes back. You can proceed to the class because this
Yes.
part I just have I'll complete and upload the video. You can later on listen. I have made
Okay.
an announcement. You can proceed. Those who have got class, please proceed. And we'll again meet at 11 o'clock. Right?
Okay.
Okay. So unit step, unit impulse response. Unit impulse response is what let us see. So then it is going to be your R of S is simply 1 by Ts plus 1 is transfer function multiplied by my input that is going to be simply sorry, this is CFS. I'm just making a mistake. CFS is equal to into R of S. So R of S happens to be 1 for unit impulse function. So it's simply 1 by Ts plus 1 is what is my CFS. So this is what is the best method of doing any experimentation. So when you give an unit impulse as an input, whatever the output response you get, the transfer function itself. So its transfer function in equivalent in time domain is what is called unit impulse response function, and that is useful for predicting the nature of that straight away, your system nature. And also it would be more appropriate if the system is subjected to shock loads, right? So see now I would rewrite this in a convenient form to apply my Laplace inverse Laplace transform. So I will take t out, 1 by t out. So if I take that out, it is going to be 1 by s plus 1 by t, right? So now C of t would be Laplace inverse of C of s, and that is going to be this 1 by t as it is, and this is 1 by s plus this, so it is e raised to minus t by t. So this is what is my response for all values of t greater than or equal to 0. So when t is 0, what is the value that I get? So C of 0 is what I get is 1 by t into e raised to 0, that's equal to 1 by t itself, 1 by t. So what is as t tends to infinity, C of infinity, t tends to infinity, 1 by t e raised to minus infinity, that's going to be 0. So if you look at this response, it would be appearing like this. It would be appearing like this. So take time on this, and then you have not R of this output. So C of t here. So what is that? I'll have at t is equal to 0, it's 1 by t. And t tends to infinity, it is 0. So you would see this function is going to be like this. exponentially decaying function. Exponentially decaying function. So this is what is your C of t, that's equal to 1 by t e raised to t by t function. So this is what is called the unit impulse response function, right? It is decaying because e raised to minus value that you have, and you would have this variation from 1 by t to this. So now, interesting aspect here is for an LTE system. This is very important conclusion or observation from all these three cases. For LTI system, linear time invariant system, this is applicable that I have this function, input functions, R of t, for R of t equals t, t greater than or equal to 0. I had my C of t, what was it, t minus t plus t e raised to minus t by t. So this is my ramp function. When I had my input function as unit step function 0 and t less than 0, it is 0. When I had this function, my response C of t had comes out to be 1 minus e raised to minus t by t, and R of t happens to be Dirac delta function. When I considered for t greater than or equal to 0, I had my output function C of t as 1 by t e raised to minus t by t. So these are going to give you an interesting observation that the first function is the unit ramp function. If I differentiate this function, I get my step input function. If I differentiate this further, I get my unit impulse function. If that is so, I can also do a differentiation of my response. I'll get my output response, and that is applicable for only LTI system. So if I differentiate this, I'd get 1 minus, this is going to be constant, so it's 0, and here it is going to be minus of t into 1 by t that goes, so I'll get this. So differentiating this function, I would get this function. And if I differentiate my output response here, I get my this. So if we are having response conducted through the test, for example, you take your vehicle and you give your unit step steering input and you got your response, and your system analytically is represented as an LTE system like bicycle model, then what is that you would do it is output response that you have, you can simply differentiate to get your system characteristic function, that is unit impulse function, and take its Laplace transform, you get your transfer function, vice versa. Or you can integrate it to get your system behavior for your response for ramp function. So this relationship holds good. If I do one test, I could get the response correspondingly what is going to be for the remaining two tests without conducting, and that's only applicable for LTA system. So this is what you should understand, and for non-linear system this relationship will not hold good. For non-linear system cannot have this property. This property. So what is this property? You understood, right? So the property is, if I have my standard input functions like ramp function, unit step function, and unit impulse function, which could be obtained, which could have a relationship by differentiating ramp function, I get step function, differentiating that I get this. That same holds good if I have the corresponding outputs with my calculus. So I can differentiate response of my ramp input to get my step input response, differentiate it further to get my impulse input response. So with this note, I'll stop today's class, this morning session. And again, we will meet at 11 o'clock to continue with this. Right? If you have any specific doubt, I would answer now. Otherwise, we will stop this morning lecture. Any doubts? Specific doubt? No. So I stop recording.